Hello everyone, my name is Etienne Lesage. I'm Senior Product Manager in the Speos team.
Hello, Sébastien Mag. I'm a Senior Product Specialist also in Speos team.
Hello, I'm Wang-Fei Nguyen. I'm Image Science Director, Product Owner of the Analyzer product line solution at DXOMARK.
So today's presentation will be about how Ansys, Speos, and DXOMARK Analyzer join forces to revolutionize the virtual camera system validation. And what I propose is to start introducing the two companies, and then we'll go through the work we have been doing on this validation process. So let's start with Ansys. So if you consider the simulation inside the digital transformation aspect, its part has been growing with years, I would say, and since it was several years ago only used when doing the detailed design and optimization of new products, now it can be actually considered from the start when you are actually planning a new product and working on the original initial concepts. And it can also goes until the end of life of the product, obviously. So what we actually aim at is to really provide the simulation tools to make sure that your virtual prototype will be as accurate as possible when comparing them with the real ones. And obviously, the less prototypes, real prototypes you will do, the best you will gain in terms of time and obviously in terms of money. So if we look at what Ansys proposed in terms of solutions, so obviously we aim at addressing lots of industries with different solutions, applications. Obviously today when we talk about platforms, we talk about materials, but also cloud HPC. Optimization is really key when you do the design of a new product. Obviously, the simulations will generate a lot of data that will need to be managed. And I will just give you a few words on the multiphysics. So multiphysics is really key since Ansys has a unique portfolio in terms of simulation solution to handle different types of physics. So you can see here structures, fields, electronics, semiconductors. So everything can actually work together thanks to the multiphysics approach, platform approach we have. And what we will really focus on today's presentation is mainly the optics parts. That includes the conventional optics, but also the photonics. So I will go into the details to the next slide, sorry. When we talk about Ansys optics solution, we talk about multiphysics, I just mentioned, and multi-scale simulation solution, starting from nanoscale, where you will actually be able to perform photonic simulations thanks to Ansys numerical. Then you will be able to design the components moving to the macro scale, let's say, with Optics Studio. And then once your component is well defined, designed and optimized, you will be able to integrate it into Ansys Speos for considerations of environments, for instance, real environments, lighting, and so on. If we focus a little bit more on what's going to be today's topic, the virtual camera validation, Ansys proposes a unique workflow that starts with a 3D scene, virtual scene, in which we will define the optical properties, the lighting conditions, and so on, but also the environmental effects, such as rain, fog, and so on. Since the products are integrated into a CAD platform, we'll be able to consider complex geometries such as a car, as you can see here, a parking lot, and so on, and position, as I mentioned, the different lighting in the scene and apply the different optical properties and place the different sensors. So that really defines your 3D scene. So then, if we consider the virtual camera validation, we need at some point to have a virtual camera inside the scene. This can be done thanks to the Optic Studio software that permits to export a reducible model from the lens design that can then be used by Speos to create a virtual camera sensor and make the virtual acquisition. From this virtual acquisition, we need then to convert the received signal into photons into electrons, electrons into a digital signal, and eventually this digital signal can be processed, developed using the processing parts of the software. So everything can be done using the different tools provided by Ansys along the chain. Now, if we consider some more, even more details about the different parts I just mentioned, regarding the lens parts, so I mentioned a reducible model that can be generated from Optic Studio. So basically, the way it works is that we capture all the optical properties, optical effects of the lens system, all the characteristics of the lens system, capture that, then export that into a reducible model that can then be used by Speos to actually reproduce those characteristics inside the 3D scene, as I just mentioned. From the characteristics, you can see here, we can account for depth of field, distortion, resolution, and so on. So that's actually quite an accurate reducible model. And since it's a reducible model, it allows to perform really fast simulation. Then, if we talk about the sensor parts of this camera model, the sensor part is based on the standard that is named EMVA 1288. That describes actually the physical model through a mathematical model. And the way we actually account for this standard in Speos is mainly the other way around. So we use basically the mathematical model to basically get the physical parameters of the system. So if then I mentioned the reducible model for the camera sensor, but in some cases, and you will see that later in the presentation, we need to consider the complete lens system. So it includes the lenses, as you can see here, but also the optomechanics that constrain mechanically the lenses altogether. So if we have a camera here, the camera will actually provide an image from an object. So for instance, a source, and there will be different effects. So obviously the first one is the ideal ray path. So the ray path that has been used to design the optical system in order to provide the image of the object through the lenses. But in real life, it's not as easy as it seems. You may have some lights that will actually interact with the different lenses, the different diopters, and being back and forth reflected, transmitted inside the lens system. That will actually cause what we call the lens flare. Then you have the mechanics. The mechanics are not purely absorbing the lights. They may scatter the lights and also introduce some causes of stray lights. So that's the scattering, mainly from the optomechanical parts. And finally, you also have some scattering of the light on the sensor itself. So the sensor is quite a complex structure that can actually scatter back the light into the system. And then you can also have some reflections between the different diopters that will actually introduce some scattering effects. So we can move on to the DXOMARK presentation.
Thank you, Etienne. And so now let me give you a few words about what is DXOMARK. So if you can move on to next slides. So DXOMARK is basically a 20 years old test lab solution provider and test house. We started in 2003 with the launch of DXOMARK Analyzer, which was image quality testing software and hardware solutions. Then in 2008, we launched the DXOMARK.com's website, on which we published all the results of our DSLR and lens testing. In 2012, with the advent of the quality on the smartphones, we launched the smartphone camera testing benchmarking on our website with all the results that were available at the time. And since then, of course. In 2017, we have DXOMARK became a fully independent company. That was one important step to make sure that for everybody that our benchmarking and results are totally independent and reliable. We expanded our scope in 2020 with the display testing protocol, which is very close to general image quality analysis. In 2021, we added to our portfolio additional automotive products and services. And in 2023, we also added webcam and video conference solution protocols. So overall, this means we have more than 20 years of expertise built over all the benchmarking that we've done and all the system that we've developed. So next slide, please. Here are the products and services that our company offers. First, we have the benchmark and testing, which is leveraging all the testing expertise to help our customers understand the quality of their device and how to improve them, also in comparison with other devices that have been tested and that we can test for them. To help for this benchmarking, what we do is that we developed lots of hardware and software internally, so as to be able to generate all those results. And we do provide all these equipment and software to all customers. And last, we have the academy, which consists in trainings and courses for people willing to improve their knowledge and skills in image quality. Next, please. So overall, what is the team of DXOMARK? We are more than 100 people, including more than 70 dedicated for just image quality evaluation. Those people are split basically into two main teams, R&D and benchmarking. And this helps us test more than hundreds of devices each year. Next, please. So what is Analyzer inside DXOMARK? So Analyzer is what we could say the R&D for the image quality. It's providing from hardware to software and from unitary measurements to full automation in the lab. We are building it so that it's reliable, reproducible, and repeatable and easy to use for everybody. It's also done so that it can cover all types of application from the DSLR that we started with in 2003 to the latest smartphones, drones, and AR, VR, for instance, that we can see more and more discussed at the moment. Also, what we do is that to always stay at the latest point of the advance of the technology, we update our solutions from 2 to 3 times a year, so that you have the latest evolutions inside our solutions. Next, please. So how does it work? What do we provide? We can provide services and tools to help our customers from writing specifications to the mass production manufacturing of their devices. So we cover all those aspects with our expertise that we've built over all those years working with lots of people and lots of devices. What we do provide are tools and services from measurement reports and tools for their labs. So this brings us to the next point. Please, next slide. So initially, we started with testing in the lab, so the R&D testing, and we expanded to production line testing. So from the lab to the manufacturing. And now what we're doing is that we're expanding with the partnership with Ansys into the simulation part. So integrating all the simulation, the very first part of the camera designs. And so, Etienne, if you want to go next.
Yes. So thank you, Phi. So basically, what's really key for us in terms of our relationship here is to provide a way to have extreme predictive accuracy when looking at the simulation results. So it's not only a simulation results that you will analyze using the let's say the conventional Speos measurements you can do today. It's also a way to make those simulation results as close as possible to what you will obtain using the real system, measuring the real system thanks to the DXOMARK analyzer outputs. So those outputs are basically based on physical metrics, and they could be considered during the product development phase, and eventually identify potential problems. So that's really key for us to account for that as early as possible in the design at the design stage, all the stages basically when simulation is needed. Also, since we are considering a virtual environment, a virtual scene, it's easy to replicate this scene. So we just need to reuse the same scene from one project to another. Eventually, you'll be able to vary the lighting conditions, the objects you want to see in the scene. So at the end, it provides you endless possibilities for scenarios. So I would say that only the imagination is a limitation. And since we are using the simulations, everything can be automated, and everything will run at the speed of simulations.
Okay, so what is the scope of today's presentation is to show how those simulations can be integrated into what we at DXOMARK call the automotive camera report, which consists of testing a lot of physical properties of a camera module. And so now the idea is that to be able to simulate a lot of those elements ahead of the production of the camera module. So the first three elements that we will be discussing in this webinar are first the lens model, which is the distortion, and then we have the lens flare, accumulated with also the sensor and camera module itself. And we'll have also the dynamic range of the sensor that will be analyzed here. So now we can start with the distortion measurements. And so next slide. So the distortion, we will first start by explaining how we measure it. So here at DXOMARK, we do that using dot charts. In the image, you can see two that we have. And let me now just give you an example of real charts. So yes, so for scale, this is the smallest one that you could see in the image. This one is made out of glass, and the precision in the flatness is less than 1 millimeter over the whole surface. We have the biggest one that you could see also on the image earlier is made out of aluminum honeycomb and has the same quality in terms of flatness. And we can make also smaller ones for all types of applications and camera configurations. So those, so Etienne, if you can share the slides again. Okay, so those dot charts are following the standards ISO 17850 about geometric distortion and the IEEE 1858 CPIQ standard, which we helped both write. And so along with the outputs, I mean the metrics that are defined in the those standards that we do follow and output, we also generate the distortion models that are used to fit the distortion and to understand how distorted your camera is. And these models are the Brown-Conradi ones, using either 5 or 12 coefficients. And the formatting is similar to the one used in OpenCV. So they can be reused very easily. We also have X and Y polynomial model for a much more complicated distortion. So if we're going to go to the next slides, I will explain you why. So for instance, here we have the I would say a normal radial distortion, which has some slight decentering, and we can see that the OpenCV12 coefficient was the model that had the best fitting inside. We can see also the all the different outputs that we generate, so the TV distortion, which is very helpful for people in normal, I would say in photography. We have geometric distortion, we have the CPIQ distortion, and then we also have the distortion curves. And if we go to the next slide, so this one is a camera system that has a cylindrical lens, and so the distortion is non-radial in a sense. And we can see that here the OpenCV12 and OpenCV5 models were ill-fitted, and that the polynomial model was much better, which is here showing a very low error in the fit. What we can see here also is that we output some specific metrics, KPIs, which are the vertical, horizontal, and diagonal directions for the distortion, showing you that the distortion is different in all those directions and how much it varies. So this helps a lot for the analysis. And so how does it can it be applied to the simulation from Sébastien?
Yeah, so now I'm going to explain you what we did on our side. So first of all, we took a lens design done in Optics Studio, and from this lens design, we add the distortion curve. And we exported this lens design to Speos using our reduced order model. And then in Speos, we added the matrix of dots in front of the camera. And we perform a simulation on that to get the results, which is irradiance in front of the sensor. And we send that to a DXOMARK analyzer in order to compare the distortion curve, the initial distortion curve, the reference from Optics Studio, and the results from DXOMARK analyzer. And the target was to see if the correlation is correct or not. Tu as sauté. Okay.
Yeah, so it's
like yeah.
that's Sophie.
Click.
Yeah, so here, sorry, I forgot to unmute myself. So here are the results for the simulation, for the measurement on the simulation provided by Sébastien. So we can see that this image has a very distinctive distortion variation, which is first barrel then pincushion. And so this can be seen well on the TV distortion measurements, where there is a change in the sign of the TV distortion when it changes from a barrel to pincushion. This is also seen on the CVPAQ distortion measurements, where we can see the variation going up and down there. And in this case, we have the OpenCV12, which was the best fitted, which means that there are some little decentering that were measured due to the positioning of the dots not centered in the image, probably.
Okay, so now the graph on the right gives different results. So first of all, the green spots are the original data from Optic Studio, whereas the orange circle are the result from the DXOMARK analyzer. And the blue curve gives the difference between those two results. We can see that the correlation is about or better than plus minus 3 pixels, which is very good in this case, taking into account the fact that we just use the three main coefficients from the Braun-Conradi model. And so now we can switch to the other bench we work on.
Yeah, so now it's the dynamic range, so analyzing the quality of the sensor itself. So recently, what we've seen is a real improvement in the quality of the image sensor technology, especially in the automotive domain, where we've seen sensors that were able to output up to 24-bit in their images. And so what we saw in the IEEE P2020 automotive standard group is that the existing solution to set up, existing setup and solutions to measure dynamic range were not enough. So we decided to build a new setup. So let me show you now the live setup. And you can switch, yeah. So this setup is made out of 4 light sources. The main big light source here enables us to go up to 1.6 million candela per meter square. And we can change between 4 patches here. And we have 3 other LED panels that can go between 500 candela per meter square to 15 candela per meter square up to 65,000. However, with the charts that we put on the LED panels, we can go even lower than that. So this means that on this LED panel and here, the darkest patch has a difference of 170 dB compared to the brightest patch of this light source. What is interesting also is that the dark patch here are not symmetrically positioned compared to the very bright ones. So we don't have the ghosting, the direct ghosting of those patches on the very dark ones. And we only have those elements that are across each other because they have similar type of lighting levels. And so these, what we also design is that we have a 2-to-1 contrast on the different elements so that we can measure the contrast and evaluate whether or not the contrast is visible or is distinguishable between the different patches or all over the dynamic range of the chart. So let me go back to the slides now. So next one, please. So how do we evaluate the dynamic range on this setup? As I mentioned, we need to evaluate how the contrast is distinguishable between the different patches. And to do that, so we are looking at the contrast to noise ratio, which is the difference of the signals between the two patches over the square root of the noise variances. If we go to the next slides, please. So the dynamic range is the ratio between the maximum luminance over the minimum luminance for which we have the contrast to noise ratio that goes over 1. And so we compute that in decibels, so in 20 log of the ratio. And this is what is defined in the IEEE P 2020 dynamic range clause of the draft. So for the simulation, Sébastien?
Yeah, so on our side, we first model the light source geometry, and we put on each small square the luminance given by DXOMARK. Then we did a simulation using Speos to get the exposure map. So that's the data just in front of the sensor. And then we post-process this using SSS exporter to get a raw image. The raw image is in relation with the sensor properties following the EMVA 1288 model. So from that, we have the raw image. We can send this raw image to the DXOMARK analyzer. And now we'll see if we have a good correlation between the properties we set in the sensor and the result from the DXOMARK analyzer.
So when we input the image from the simulation inside our software, what happens? First, we have an automatic detection of the charts and all the different lighting systems and of the different regions of interest that are located on the patches. So you can see that on the left first for the detection of the charts, and then on the right for the positioning, automatic positioning of the region of interest on each patch. So next slide shows the measurement results themselves. So the sensor that Sébastien simulated came with the datasheet that says that he has a 7.2 dB dynamic range. And in our measurements, you can see on the graph on the middle, the bottom middle, that the contrast dynamic range is about 72 dB with the values written just above the graph. And so the correlation is very good and is within the error of the measurements, which is the step between the different patches. And in this case, it's about 3 dB. Okay. So now we go for one of the most complicated parts, at least for the simulation, I believe, which is the flare. And on our side, so can we move to the next? So for the flare, we have let me show you the system itself directly. So we have created a full system to test the flare on the camera system. Here it's showing how we test it on a smartphone, for instance. What is it made out of? So we have a very powerful bright source that is collimated at infinity on a rotating arm. We have the positioning of the camera system on a 6-axis head, so that the camera can be positioned exactly at the center of rotation of the light sources. So here you can see if I make the rotation of the system, it will go all around. And the system is done so that we can rotate 320 degrees around the camera system, meaning that we can also test, for instance, 200 degrees field of view camera systems. So the light source is designed so that we try and mimic the most common point light source in the wild, which is the sun. So basically, it's about less than 1 degree of apparent view angle. So let me go back to the slides to give you a bit more details. So if you can go to the next slide. For the light sources, so here is the visible light sources with apparent diameter about less than 1 degree. So, and also what is important is a very bright light source. So we have more than 10,000 lux measured at the lens surface, and the spectrum is in the visible. So for most visible system, this is sufficient. But then we know that there are some people who want to test in the near infrared. So if we go next slide, shows the another light source that we have, which is the 850 nanometer. And then the next one is the 940 nanometer light source. And they have much more light power than the visible light source itself. So if you want to test how lidars and other type of NIR light sources are impacting your imagery, you can use those light sources to test that. So this was for the hardware part. Now the measurement itself. So we designed this hardware with the software in mind. And we push also these formulas to the IEEE P2020 flare draft, and also it will also be part of the ISO 19844 point light source part. So how do we measure the flare? Is we use the sensor as a light meter, and we evaluate the flare as an equivalent illuminance in the scene. So, and we will compare the level of this equivalent light source to the illuminance generated by the light source itself. So that can be seen in the next slide. This is what we call the flare intensity, which is now expressed in decibels, the 20 log of the ratio of the illuminance due to the flare over the illuminance of the light source itself. And so the lower the value, the better the quality, and so the less the flare. And we can move on to the next slides for the simulations from Sébastien.
Yeah, so on Speos side, we first model the light source with the same properties as what we saw just before in terms of spectrum, power, divergency, uniformity, and so on. And also the capability to move around the camera. Here we did we splitted the simulation into 3 parts. The flare effects of the stray light from the lenses, stray light from the mechanical parts, and stray light from the sensor itself. then those three contributions, so we did that in order to be more efficient regarding simulation time, and also to have more capability to analyze the different results and the different contributions. So then we added the three contributions into one global contribution to put that into the SSS exporter. And from the SSS exporter, we output here two types of results. The developed image in order to have a visual rendering of the flare, and also a raw image to send that to DXOMARK analyzer to get quantitative data. So this is the first simulation, the first contribution, due to a reflection on the lens, the optical part of the lens. That's mainly due to non-perfect coating we may have on the lens. And here we can see one example of additional sequence, but we can simulate a lot of those sequences. So here we can see play the optical flare versus the incidence of the light source. Now, now this is the second contribution. So from the optomechanical part, we can put BRDF properties on surfaces. So we can describe the way the surfaces may reflect the light into the system, and we can get the contribution of this true light on the sensor. And the final contribution is from the sensor itself that can diffract and reflect the light into the lens system. And due to reflection on the lenses, a part of the light can go back to the sensor and add parasite lights on the final image. So here we have three examples of each, one example of each contribution that is added to get the final result. Here it's the result for 25 degrees of incidence. So the spot is inside the field of view of the camera. Here we mainly have contribution from the optical part and the sensor. Whereas for a light source at 50 degrees of incidence, the main contribution is from the mechanics. And now we are going to see some analysis from DXOMARK.
Yeah, thank you, Sébastien. Here, as we mentioned, so this is the output from our measurements. So it shows in dB the evolution of the flare in the field of view. So for instance, here it's with the flare at 0 degree in the field, so at the center of the image. So we can clearly see the flare that is really high around the light sources and then decreasing as we go out of it. And this shows well in the cumulative distribution function, showing the number of pixels that have a certain level of flare. If we go to the next slide, now we can see that for the light source in the field and out of the field of view, the max flare intensity has decreased a lot. We moved from 13 decibels to 41 decibel, which is a nearly 30 decibels difference. And you can see here with the same scale as before that we're really in the different level of flare. This can be seen clearly also in the cumulative distribution function, which is flat compared to what we had earlier. We go next slides.
So in conclusion, what we have demonstrated today is that we are able to use the DXOMARK analyzer in order to characterize different aspects of an optical system. So based on physical metrics. So the first one, the distortion measurements. Second one, the dynamic range, and finally the flare, as you have seen. So you may ask, okay, but what's going to be next in terms of your relationship? What you want to show us? So basically, this is not the end of the story. This is just the beginning, and what we have seen today is only 3 benches that can be assessed by the DXOMARK analyzer. The ultimate goal will be to actually address all the different benches, starting from the MTF and the chromatic aberrations, and mainly for automotive camera modules. So that's the first aspect, let's say, of where we want this relationship to go. And obviously, when you will have access to all those metrics, you will be able to actually be sure that your virtual model and the results you get from the virtual models will be as accurate, let's say, than when considering the real model. So that's the first aspect. The second aspect, so we have a lot of feedbacks from our users regarding how to get the data inside the simulation. So simulation and simulation results are as good as the inputs you will have inside the model. And sometimes, in some cases, for instance, when you want to integrate a lens system from a supplier, you don't have access to all the data to feed your simulation. So one way to go would be to use the DXOMARK analyzer to characterize those inputs. So, for instance, the distortion file, as we just presented. So we have the possibility using a real camera system to get the distortion out of it, and then use this distortion information to fill the camera model in Speos. The second aspect is the sensor part, where we can also use the DXOMARK analyzer to output the main characteristics of the sensor. So today it's relying on EMVA 1288. So we could basically use the DXOMARK analyzer output to feed the model itself, and then we'd be able to run a proper simulation with proper outputs. So that's the end of this presentation.
Thank you to our presenters for this informative presentation. As the presentation has shown, there is lots of information related to this topic. You can join the conversation and learn more on the Ansys blog at ansys.com/blog. We invite you to read, comment, and join the conversation. Okay, at this time, we'll take some questions. If you have a question about the material presented today, you can simply submit the question via the Q&A tab. This can be found on the WebEx panel, clicking on the 3 dots at the bottom of your screen, and then clicking Q&A. And I do see that we have a couple questions in the Q&A, and then we did have one question about the video and presentation slides for this presentation. I did answer that earlier in the chat, but I will just go ahead and comment that the video will be available in about a week's time on the Ansys.com website in our resource center, which is you can find that at the top of the homepage under the Learn menu. And okay, I'll turn it over to you guys to answer the rest of the questions.
Thank you. So there is the first question from John. So regarding the raw image simulation, can you provide some more detail on how the number of photons are established? So Sebastian, you want to elaborate?
So first of all, the Speos simulation result is a map, pixel by pixel. The information we have from that is the exposure. The exposure unit is in joule per square meter. then and their wavelengths. Then in the SSS exporter, this quantity is transformed into a number of electrons. Then using the quantum efficiency of the sensor and the biometrics, if there is one, we can convert that and using gain and digitalization, we can convert that into the raw image. The second part of your question is about the noise. I think it's the noise from the simulation itself. That's true that we have this noise from the simulation, which has about the same effect as the shoot noise in the reality. And this noise can affect some result or some analysis. It's quite difficult to tell you how many arrays we need during the simulation to get an accurate result, because it mainly depends on what you want to analyze. If it's just, let's say, the average exposure of your image, it's not a problem. If you want to check the dark noise or the thermal noise in your image, of course, the noise from the simulation must be as low as possible. And actually, it's always a compromise between the simulation time you can accept and the precision of the results you want or you need.
So maybe just to mention regarding the simulation time, that you can actually reduce it by using GPU acceleration. So that's one thing, and the other thing is maybe to use HPC if you have several computers available to run your simulation.
And if I don't answer correctly or completely your question, please contact me directly, and I will try to add the information.
Thank you. So there is a second question. I would love to understand more about the sensor modeling for the simulation context. How detailed is it? Is it purely based on literature models, or do you get sensor design information embedded in Ansys tools? So I guess there are the two aspects are actually true. So from the literature, that would be mainly the EMVA 1288 part. So basically from the spec sheet, you can find your sensor reference. You can actually access most of the parameters. The second aspect will be also to use simulation. So we mentioned at the beginning inside the Ansys Optics workflow, Ansys numerical. So you have the possibility to design all the stack, the different layers that define your sensor, and run simulations. And from those simulations, you will be able to use some outputs in order to feed the model. So for instance, the quantum efficiency, as we mentioned, and some other parameters. So actually, both solutions are possible.
And just one precision, in the literature, the quantum efficiency is only given versus the wavelength, whereas using our software numerical, the quantum efficiency is modeled as a function of the wavelengths and also the incidence of the light on the sensor. This second dependency is really important, mainly in case of sensor with micro lenses on each pixel.
Okay, there is another question regarding the significance of doing correlation between original measurements and simulation results. So, if I understand the question right, so really the key point is to provide the same metrics, the same physical metrics on the virtual design than the one you will get making measurements on your real system. So you can obviously wait for the real system to be prototyped and manufactured. But then it will be, if you find a problem at the end, it will be a waste, let's say, of time and money. So the best will be to make sure at the virtual system level that you do not have any issue, and your virtual prototype give good performances. And this is actually true, even more true, let's say, using the DXOMARK analyzer measurement capabilities. Look, Fee, do you want to add on this?
I'm totally aligned with you. I mean, the main goal of those simulations and the work we've been doing here was really to make sure that we have good correlations between the simulation and reality in the end, so that people could at some point bypass all the real measurements in order to gain a lot of time in the test labs at some point. Because as was briefly mentioned earlier in the presentation, some of the protocols that we're doing are really time consuming, and sometimes it's difficult to reproduce some specific conditions. For instance, if you want to add rain or something like that, or fogs, or inside your testing systems, this is not something that you can easily do in the lab. So being able to do that via simulation and making sure that the results are correct is very important. Right.
I agree. So the next question is about the input format for the DXOMARK testing software and for Ansys. So correct me if I'm wrong, but you basically used a raw image.
Raw image, or for the moment, we don't define a specific transfer file for the moment. So we basically use a standard way to save the NumPy data.
So yeah, to be clear about that, so our software takes as input raw files, and we can modify, I mean, not modify, but we can convert any raw file into, any raw file for which we would have description of the content into data that we can analyze. And so this is what we did initially with the data provided by Sébastien. And just then, for clarity, we moved on since Sébastien was using Python, and we're also using Python. So we can use Python data to make the measurements. It's very easy. But otherwise, our software takes as input JPEGs, HEIC file, raw files, DNG files. So we can take lots of different input as long as they're written following the standards that they are supposed to follow.
Mm. And so on your side, basically the Speos sensor system exporter, so the TSSS exporter Sébastien mentioned during the presentation, is also able to generate
Python data.
Yeah.
And raw image as a DNG format, and also develop image as a PNG or JPEG. And also IKEA.
Yeah. Okay. Final question regarding the creation of camera sensor in Speos. So the origin of the camera sensor basically corresponds to the image location,
not the lens.
Not the lens itself. So you need to account also for the size of the lens system. So basically, if you put an object too close to the camera sensor, you might have some issues.
Okay, that is all the time that we have for questions today. We'll follow up with the rest of the questions by email in the next few days. Thank you to all of our presenters. This concludes today's webinar. On behalf of Ansys, I'd like to thank you for your attendance and wish you a good day. Thank you, everyone.
Thank you. Have a good day.